Two important theories have been developed to explain the properties of acids, bases, and salts. These are the Arrhenius theory and the Bronsted-Lowry theory. Here we'll look at the Arrhenius theory. In 1887, a Swedish chemist, Svante August Arrhenius, proposed that an acid is any substance that releases hydrogen or H+ ions in water. An example is the gas hydrogen chloride, HCl. Looking at the Lewis structure of hydrogen chloride, we see that there is a covalent bond between the hydrogen and chlorine atoms. They are sharing a pair of electrons. However, the bond between hydrogen and chlorine is quite polar, and although it keeps the atoms together in the gas phase, when HCl is added to water, this bond is too weak to keep the H and the Cl together. When HCl is added to water, the molecule breaks up. The chlorine atom, being more electronegative than the hydrogen atom, takes both of the shared electrons with it. Because the hydrogen atom has lost its electron, it acquires a positive charge. And because the chlorine has gained one electron, it acquires a negative charge. It is now called the chloride ion, or Cl-. This whole process can be summarized by the equation HCl gas gives H+ aqueous plus Cl- aqueous. Aqueous means that the ions are surrounded by water molecules. So Arrhenius pictured an aqueous solution of HCl as a collection of H+ and Cl- ions floating around freely in the water. The water molecules are not shown here in order to keep the diagram simple. Water is given a blue color in this diagram. Because this is a water solution, the subscripts AQ for aqueous are used for the hydrogen and chloride ions in the equation. According to the Arrhenius theory, a base is any substance that releases hydroxide or OH- ions in water. An example is solid sodium hydroxide. Because NaOH is an ionic compound, solid NaOH is composed of a crystal lattice of sodium and hydroxide ions. Here we show a 2D representation of a few of these ions. When a piece of solid sodium hydroxide is placed in water, the polar water molecules attract the ions and pull them away from the crystal. This process is called dissociation. The dissociation of NaOH is shown by this equation. NaOH solid gives Na plus aqueous plus OH minus aqueous. So according to Arrhenius' theory, an aqueous solution of the base sodium hydroxide could be viewed as free and mobile Na plus and OH minus ions surrounded by water molecules. The other type of ionic compound Arrhenius defines is a salt. A salt is an ionic compound that releases a cation other than H+ and an anion other than OH- in water. An example is the common salt sodium chloride, NaCl. NaCl dissociates into Na+ ions and Cl- ions. So a water solution of NaCl would contain mobile Na+ and Cl- ions. A few Arrhenius acids are shown here. Notice their formulas start with H. This is the hydrogen atom they lose as H+ when they dissociate in water. In acetic acid, which is often written as CH3COOH, the H that the acid loses is written at the end of the formula instead of the beginning. Organic acids are often written this way. You just have to watch for the COOH at the end of the formula in order to recognize these as organic acids. A few Arrhenius bases are shown here. Notice their formulas all end in OH. This OH is lost as a hydroxide, or OH- ion, when these compounds dissociate in water. The cation in the base must either be a metal or the ammonium ion, NH4+. Let's have a look at the compound CH3OH. It's called methanol, or methyl alcohol. At first it may appear to be a base because it has OH at the end of its formula. However, CH3OH is not a base. The structure of methanol can be represented like this. The bond between the carbon and oxygen is a strong covalent bond, and it is not easily broken. Therefore, an OH- ion is not released by CH3OH in water, and neither are any other ions. All the covalent bonds in methanol are too strong to be broken by water. Methanol is a molecular compound that does not dissociate into ions in water. So we can now summarize by saying that compounds in which OH is attached to a carbon atom are not bases. Some examples of these are alcohols like methanol, ethanol, or 1-propanol. And remember, compounds whose formula ends in COOH are organic acids, and therefore are not bases either. It should also be noted that a compound called phenol, C6H5OH, dissolves in water, but it is not a base. In water, a few phenol molecules will lose this H as an H+ ion, and the negative charge on the resulting phenoxy ion, C6H5O-, is stabilized by the presence of the benzene ring. The presence of free hydrogen ions means this is an acid, and because it produces hydrogen ions rather than hydroxide ions, we can state that phenol with the formula C6H5OH is not a base. In this column of the table, we see some salts. Notice they are all ionic compounds that neither start with H nor end in OH. The last one, NaCH3COO, looks like it's organic. However, since it starts with Na, we know that it must be a salt. We can find both Na+ and CH3COO- on the ion table. So we know that NaCH3COO, called sodium ethanoate, or more commonly sodium acetate, is ionic. And because it doesn't start with an H or end in an OH, it is an ionic salt.